All right, so Unit 19, limits, Section 19.1, limits of functions. These next two units that we do are vital for the beginning study of calculus for those of you that are moving on. Okay, so think to yourself what a limit means, or think of the definition of a limit, or what word pops into your mind first. When we talk about limits in terms of functions, three things I need you to associate with a limit. Limits are y values. Limits are approach statements. And you'll hear me use as x approaches. As x approaches, you'll hear me use that a lot. And limits are both unique and finite. Okay, so those three things I'll continue to refer back to throughout the course of Unit 19. All right, the limit as x approaches positive or negative infinity. So here we are, okay? This is interpreted limit as x approaches infinity, and here's my function, 1 over x. So when you're looking at the graph of a function, this is something that we're going to work on for you to be perfect at, because it needs to be easy for you. Okay, so as x approaches infinity, that means my x values are just getting bigger and bigger and bigger. So I'm just going to look at the half of my graph on the right-hand side of the x-axis, because that's where my x values are positive. Okay, so I'm going to highlight this. So when you answer these questions, you have to say to yourself, as x is getting bigger, what are my y values doing? What's the behavior of the graph of the function? Well, notice that your y values there are getting infinitely smaller, and they're getting so small that they're actually approaching the value 0. So the limit as x approaches infinity of that function is equal to 0. Now let's switch gears and look as x approaches negative infinity. So now as my x values get infinitely smaller, okay, I'm looking on the left-hand side of the y-axis now. What is the behavior of my function? My function is still approaching 0. Okay, so we're going to put a lot of things together throughout the next two units, but if the limit as x approaches positive or negative infinity exists, the value of the limit is a horizontal asymptote. Okay, so a couple things. Horizontal lines. We know horizontal lines are in the form y equals a number. Secondly, coming back to limits are y values, the output of a limit is a y value. So the horizontal asymptote would come from y is equal to 0. And that fact is based on the limit existed, and whatever that value is becomes a horizontal asymptote. So if we recall what we know about asymptotes, asymptotes are these lines, they can be horizontal, and we'll talk about vertical as well, that the graph comes really close to approaching, but will never actually equal. And we're going to fine-tune that definition a little bit later as well. Let me fix this one. As x approaches positive or negative infinity. Okay, so now my next one, again, I'll start here since I use green. As x gets infinitely smaller, so I'm looking on the left-hand side of my y-axis, what does it appear that my y values are doing? So my y values aren't approaching 0. Now it appears that my y values are approaching positive 1. Okay, let's look on the other half of the y-axis. So as x gets infinitely larger, okay, infinitely more positive, what are my y values doing? My y values on the other half of the y-axis are also approaching 1. So what does that tell me? Graphically, I have a horizontal asymptote at the line y is equal to 1. And if I dot that in. There's my horizontal line, and my graph for sure hugs that line. Okay. Look at another graph. So you guys try this. Limit as x approaches infinity. So you're going to look on this half of the graph. What are the y values of what's graphed? What are they approaching? As x approaches negative infinity, look on this half of the graph and try and tell me what the y values are approaching on that side. Okay, so graphically, we can look at the function, okay? I can say, all right, I'm looking on one side of the y-axis. I can look at what the behavior of the function is doing. So graphs, you have the answer in front of you. What you need to work on is where you look to get the answer. Algebraically, if we're just looking at functions, here are our rules. And at least the top-heavy, bottom-heavy equal should be vaguely familiar from Algebra 2, because you definitely studied this, or at least discussed it last year. Okay, so for the limit as x approaches infinity, you compare the degree terms of the numerator and denominator. So what's the degree? Recall the degree is the highest exponent. Okay, so you're going to have one of three categories. The limit does not exist, and the limit won't exist if the function is what we call top-heavy. So the degree of the numerator is going to be greater than the degree of the denominator, and we're going to look at examples of this. The limit as x approaches infinity will be 0 if our function is what we call bottom-heavy. So the degree of the numerator is going to be smaller than the degree of the denominator. Lastly, the limit as x approaches infinity is going to be a non-zero number if the degrees are equal. So the degree of the numerator is the same as the degree of the denominator. These cases where it equals a number, okay, according to what I wrote up here, if the limit as x approaches infinity exists, the value of the limit is a horizontal asymptote. So these two cases where the limit equals 0 or the limit equals another non-zero number, these would tell you have a horizontal asymptote at whatever the value of the limit is, okay? Either 0 or the other number. And then lastly, limit as x approaches c of a constant is that constant. So limits are y values. This is the function. So think about this. If my function just equals a constant number, then its graph is just going to be a horizontal line. So no matter what my x value is, anywhere on the line, its limit is going to be that corresponding y value. Okay, so let's look at some examples. The limit as x approaches positive or negative infinity, and we're going to use our comparisons here. So I'm going to compare the degree of the numerator with the degree of the denominator. There's only x's in the denominator, so this is what we would call our bottom-heavy function. And the limit as x approaches infinity is going to be 0. And hopefully you can see that. If my denominator is infinitely larger than my numerator, bigger denominators make smaller fractions. So my y values are going to get infinitely smaller, infinitely closer to 0. So that's why bottom-heavy has a limit of 0. All right, highest exponent in the numerator is x cubed. Highest exponent in the denominator is also an x cubed. So this is what an equal would look like. Okay, the degree of the numerator is the same as the degree of the denominator. So the limit is just the ratio of the coefficients. Okay, so the limit of the example number 2 is 2/3. So what does that tell me? There'd be a horizontal asymptote on that graph at y is equal to 2/3. And likewise over here, I would have a horizontal asymptote at y is equal to 0. All right, next one, highest exponent in the numerator is x cubed. Highest exponent in the denominator is x squared. So when I compare those two, this would be an example of a top-heavy function. The limit as x approaches infinity of a top-heavy function does not exist. Okay, and D&E is certainly totally fine for what we need. The last one, highest exponent in the numerator is x squared. Highest exponent in the denominator is x cubed. So this would be an example, another example of a bottom heavy. And regardless of what the coefficients are, that limit is 0. Graphically, we would have a horizontal asymptote at the x-axis, at the equation that line y is equal to 0. Okay, I'm going to stop the first video here. And I'll post another one for the remaining notes.